Alright, welcome to the hybrid activity for Chapter 9. We're going to try to explain how to use a point particle system and a real system to analyze a problem. So here we go. Let's cover the definitions of a point particle system again and the steps we're going to need to use to apply these ideas. So the whole idea of a point particle system is it has the same mass as a real multiparticle system, but its mass is condensed into a point particle located at the center of mass of the real system. For a point particle system, we have the representation here of the rate of change of the system's momentum should equal to the net force acting on the system, and we also know that the change in translational kinetic energy has to be equal to the work done by the net force on our point particle system. And we can represent the change in translational kinetic energy also as 1/2 the total mass of the system times the... Here's how we're going to start to analyze our system. The first thing is you can imagine crushing the real system and its forces down to a point at the center of mass of the real system, including moving the tails of the force arrows to the point. Draw a diagram of the initial and final states representing the point particle system as a dot and showing all the forces acting on the real system. So here's what we're going to do. The question here is, to what distance did the force act on the point particle system? I believe we did this in class, but I want you to try and venture a guess here for this answer. Alright, so let's find the center of mass of the initial system. So here is the initial state of the system, and the center of mass will be located right here. Let's find the center of mass in the final system. Here we go. Now the assumption, which is not stated in this problem, are the mass does not change from the initial to the final states, and both masses are equal, and the mass is of the spring is very small. So the center mass of the spring should be right here in the middle of the spring. Alright, so where are they located? Well, we can locate them by these gray lines and then find their position by taking the average between the two known positions of each mass. And so we get 0.07 or 0.03 and 0.1 meters. So if we take the difference, so basically we can ignore the rest of the system now and just look at this. Alright, so now what we're going to do is place the tails on all the forces and place the tails of all the forces on the point particles itself. So to do that, we would have this. There's our force F on both of them. And so the idea is to figure out how far this is going to travel in the point particle system, and it would travel this distance. So in our case, the correct answer for this would be 0.07 meters. So now we're going to calculate the energy principle for the point particle system. And remember, the only energy term that will be in there, since this is a point, everything else is external to the system, so then all we have is our change in translational kinetic energy. Alright, so here's our point particle system. What is the change, or what is the energy equation for this point particle system? I want you to venture an answer. Okay, so we have to figure out the work done by the external force. In this case, the external force is our force F, and that moves the point particle a distance of 0.07 meters, and the displacement is in the same direction as the force, so the work done is positive. So the correct answer for this is answer 1. Alright, here's another point particle system, and I want you to try to figure out what is the work done by the external forces on the system with the hand pulling up with a force of F. and we are on the surface of the Earth. Alright, so you've applied your answer, so let's go through the steps in finding the answer. We need to find the center of mass of our systems. There it is. We need to find the distance it's changed. And if we look at this and you analyze the problem, they should have changed a distance b here. And then the next step is to put the forces on the object. So we don't need the picture anymore, we just got a point particle. And so there's a force pulling up of F, and there's a force pulling down of the weight force caused by the Earth acting on our box. So if we calculate the work done by our force, each force, it says force F moves the force a distance b, and the displacement is in the same direction as the force, so it's positive. But the weight force is opposite the direction, so that should be a negative sign. So the correct answer should be 1. Okay, so now we have to look at the real system to help us figure out some more answers. And we're going to do that by drawing a diagram of the initial and final states of the real systems. We're going to draw the arrows representing the forces acting on the real system. It is very important to place the tail of each arrow at the location where the force acts on an object. Alright, so back to our original problem. Here we go. So the question is here, through what distance does the force act on the real system? So I want you to figure out me a distance. Alright, so we need to figure out what the tail has traveled. So here's where the tail is located initially. Here's where the tail is located finally. And we got to figure out this distance. So assuming these masses do not change, the system has traveled a distance of 0.12 meters minus 0.4 meters, and so the answer would be 4. Okay, it's different than the point particle system. Alright, now that we have that information, we want to look carefully at how far the tails of the force arrows move from its initial state to the final state. Use this information to calculate the work done on each force, or by each force. Add up those work terms to find the work done on the real system. Then we're going to write out the energy principle for the real system, and the energy will include a term of the change in translational kinetic energy, but it may also include other terms like the change in internal energy, or the change in vibrational energy, or the change in rotational kinetic energy, so on and so forth. Once we do that, we know the change in translational kinetic energy we found in the point particle equation. We can substitute that in for the change in translational kinetic energy in the real particle system and help us figure out the change in energies of other parts of the system. So let's go and look at this. Now, the question is, what is the work done by the external force on the real system? I want you to try and answer this question. So let's go through how we figure that out. So the correct answer there would have been F times 0.08 meters. So now, what is the energy equation for the real system? So let's help us figure this out. We know the work done by the external force was F times 0.08 meters. So that eliminates answer 2 and answer 3, or sorry, answer 4. Answer 2 and answer 4. And we're left with answer 1 and answer 3. Well, which one is correct? Well, we have to include the translational kinetic energy, and we have it in both terms. But answer 1 doesn't have any other energies. So we have to, the correct answer has to be answer 3. There looks like there could be some vibrational kinetic energy and some vibrational potential energy stored in the system because the system could oscillate. So that's our answer. Alright, so now we want to analyze the total system. So we have our initial state and our final state. And from the point particle system, we found out the translational kinetic energy was equal to this, or the change in translational kinetic energy was equal to this. And from the real system, we found out the energy equation there told us that the change in translational kinetic energy plus the change in vibrational energy was equal to the work done by external forces, this. So what we're going to do is we're going to take the translational kinetic energy from the point particle problem and put it into the real particle, or the real system. And if we do that, we get this expression. And now we can solve for the change in energy associated with the vibration of the system. So if we do that, we get this expression. And if we solve that for the energy, the change in energy in vibrational system, we find out that there's this much energy stored in the, or this is how much the energy has changed for the vibrational energy component of this system. And this allows us to find how much that has changed. We know how much the translational kinetic energy has changed. And this allows us to analyze the system. So how about another example? Alright, so here's another example. We're going to pull up on the box with a we've already done this with the force F. We've done the point particle for this. What we want to do is calculate the work done by the external force. So again, we have a force F acting up, and it's on the surface of the Earth, so we have a force of gravity. So pick which answer is the correct work done by the external force on the real particle system. Well, let's figure out what work should be done on the real system by the external forces. So again, we apply our forces, both the initial and final case. That's our system. So the idea is to figure out how far the tails of those forces have changed. So the tail of the force by the hand on the block has traveled a distance of b plus a. And again, the wave force has only traveled a distance of b. Compared to, that's kind of the same distance that the point particle changed. Well, how is that going to change the work done? So if we calculate the work done, this force is in the direction of displacement, so it would be F times A plus B. This force is opposite of the displacement of B, this distance here. So that's going to be a negative mg times B. So the correct answer here has to be 4. So there's the correct answer for the work done by the external forces on the real system. Alright, I hope you're getting a better idea how to do these. Since this is in a online lecture, you can go back and review this at any time. So the next question we're going to ask is, write out the energy principle for the real system. Alright, so what is the energy principle for the real system? Just like in the last time, the translational kinetic energy is the only energy term on the left-hand side here. And that's like a point particle system, but we're doing the real particle system, so it has to have the translational kinetic energy plus other energies. Well, we notice the string gets pulled out, but we have no idea what's going on in the center of this box. So something has to be spooling this string out. And in order, so I've just called that the change in internal energy, and that can be any energy stored internally into the system. So chemical energy, rotational energy, vibrational energy. We just don't know it now. And we know the work done by the external force. We did that earlier. So we can narrow this down to two answers. It's either, no, the only answer could be is 3. This has the right work done by the external force. This one does not, and this one does not. So the correct answer has to be 3. So this is the this is the energy principle for the real system. By lifting this block up. So now let's analyze this total system now, both using the real system and the point particle system. From the point particle system, we found our change in translational kinetic energy was this. From the real particle system, we found our change in the energy of the system was equal to this. And we're going to do the same trick we did last time. Is I'm going to take the translational kinetic energy from the point particle system and put it into the real system. And if I do that, I get this expression. And now if we do some math and algebra over here, you'll find out that the change in internal energy of the system has to be equal to this term right here, the force F times the distance A. And that's how much change in internal energy would occur inside this box. Well, I hope this helps you understand the point particle and the real particle system. And we'll practice this some more in class with some other problems we'll work on. And I have a handout where you can work out in class on this too. So I'll see you in class. I'll see you in next class.